So in this video we're going to look at electron lenses. So let's first look back at what a lens should do. And now I'm going to draw the operation of the lens from top to bottom, as typically this is the orientation we have in an electron beam column. So we have a ray going on axis, which is unperturbed, and then a ray that travels further to the side should now of course be deflected by the lens, cross the optical axis, and a ray traveling on the other side of the lens should be deflected in the opposite direction to also cross the focus point. And the further outside the rays, the stronger the deflection in order to go through the same focal point. Now if we look at electrons, we can use electric fields or magnetic fields to manipulate the electron and provide a deflection. So let's first look at the electric field. So we know the expression for the electric field from Coulomb's law. So the force exerted on the electron equals minus the charge of the electron, E, times the strength of the electric field, E. So we can apply an electric field to an electron beam by using two deflector plates. So here I draw one plate, here the other plate. So we put a voltage difference over these two plates. So we connect them to a voltage source. So one plate is now at a higher voltage than the other one, which means that in between the plates we have an electric field. Say the electric field is pointing in this direction. And so here we have an electric field in between the two plates. And this electric field is everywhere. We have seen that in between two plates the electric field is homogeneous. Now what will this electric field do to an electron? Say we have an electron coming in here. So this is my electron. It travels in this direction. So it has a velocity going here. And then it enters the electric field region. Now the electric field will exert a force. And in this case, for an electron, the force due to the minus sign, the charge of the electron minus E, will be directed in the other direction as the field direction. So in this case, the electron will be deflected in this direction and then travel under an angle. Now if we look at an electron at another part in the field region, so another part of the beam, also that electron will be deflected in the same direction. It will travel through. Of course, it should not hit the plate. That is just my bad drawing in this case. But you see, in this case, with a homogeneous field, all electrons will be deflected and the beam will stay at the same beam width. So this does not provide us with a focusing field. Now that is a problem, because in this case it's not obvious from how we can exert an electric field to make a lensing effect. Obviously, the electric field should not be homogeneous. We should create an inhomogeneous field. And actually, if we think about how we accelerate and decelerate electrons, we arrive at a situation where we have such inhomogeneous fields, but there are also change signs when we change sides with regard to the optical axis. I'm going to now draw that for you. So say we have a situation where we accelerate an electron beam. So we accelerate an electron beam by applying a voltage difference. So I'm going to draw here two plates. So in a different orientation than I drew them here. And these two plates I now put a voltage difference over. So again, now here we have our voltage source. We have a voltage source here. And in between these two plates we create an electric field. So say in this case the electric field is in this direction. So an electron in between these two plates, just like here, would feel a force in the downward direction. So this means that if we have an electron beam coming in here, it will be accelerated. Now what we're interested in is what happens in this gap region. So this is the region where the beam has to pass. So let's start by drawing our equipotential lines. So our equipotential lines, of course, are running parallel to the plates here. So this one is running here. The one in the center is running parallel here. And of course, because of the symmetry, it continues being a straight line in this case as well. But here, if we move away from the center plane, something will happen due to this gap. So this is then how this equipotential line will bulge out. And of course, it will be in the opposite direction for the lower plate. So now let's see what that does to our electric fields, so which are running perpendicular to the equipotential lines. So of course, if we go on the axis in the center of the holes in the plates, the electric field line will cross each equipotential line exactly at the top. So this one, the electric field will just be directed parallel to the electric field in between the plates. So this is the electric field line on the axis. Now if we go slightly to the side, we will see that here also the electric field will be perpendicular to the equipotential line, but then because of the curvature here, also the electric field will bend a little bit and move out. And it will do so the more so if we move further away from the optical axis. So it will look like this. Here. And of course it will be exactly in the opposite direction if we move to the other side of the optical axis. Here, and here. So what does that now mean for the force on an electron? So if we have an electron coming in, let's say we have an electron on the optical axis here. So here is our electron beam coming in. The electron on the optical axis will only feel a force. Again, note the minus sign, electric force downward. So the electron here will just travel straight through and only be accelerated by the field. Now if we go slightly off axis, an electron that will come in here will also feel a force, but part of the force will be directed in the forward direction. But due to this curvature here, there will also be a small component pointing towards the axis. So this electron will also be accelerated, but it will also be deflected a little bit towards the axis. So it will go in this direction, up, and in the end here, go through the optical axis. Now, if we look at a part of the electron beam or an electron traveling even further off axis, it will encounter electric field lines that are even more curved than the one here. So that will mean that the component of the force pointing towards the axis will be bigger, so also the deflection of the electron will be stronger. So this electron will be deflected stronger and in the end also cross the optical axis. Now on the other side of the optical axis, the situation is mirrored. So the forward, if we look at a part of the electron beam at the same distance from the axis, of course the forward force will be the same, but the component pointing towards the axis will be exactly opposite sign but the same magnitude. So this electron will travel on and on, the same force exerted, so it will cross the axis in the same point. And of course here it is exactly the same but mirrored compared to this line here. So this situation will give rise to a deflection field that is increasing if we move away from the optical axis, and that is circularly symmetric, precisely what we need to get to an electron lens. Now you may say, okay, the electron beam comes in, until here everything is clear, there will be an inward directed force, but on this side everything is exactly opposite, so there will be a force pointing out. Yes, that is absolutely true, but we have to bear in mind two important things. First is that here the electron beam comes in with a big waist, yeah? So it will travel more, there will be more part of the electron beam traveling off axis, where the force is higher than here. So if we look at one ray here, a stronger inward force will be exerted here than the outward force here. So the net effect will still be a focusing, plus the fact that in this case the lens is accelerating. So the electrons go faster and faster the further they travel down. So also they spend more time in the upper part of the lens, where the inward force is larger than in the lower part of the lens. So that also gives us a net focusing effect. So in this case, the electron has undergone a net acceleration. So it's traveling at a higher velocity after the lens. So in a lot of cases, this may not be wanted. You may want to have the electron come in at a certain velocity, just provide a lens, but have the electron travel at exactly the same velocity after the lens. In this case, simply a third lens plate is added here, where the upper and lower plates are connected to the same potential, and we have the accelerating potential at the center. So in this case also, because of the reasons just mentioned, the fact that the electron beam is accelerating here and has a thicker waist in the upper part compared to the lower part, this will still give us a net lensing effect. A second thing to note is that we always encounter this situation at the source unit. So either if we have a sharp tip or a flat photocathode, we will have an extractor plate that pulls the electrons from the source and brings them into the beam, and that extractor plate obviously has a hole that functions as a first lens in our electron microscope.